Hello everyone. Have you ever heard charge, current, voltage, power or energy and wondered what exactly are these? Then this video is the right one for you. The very first topic we have is charge, and we have some definition here which states that charge is an electrical property of atomic particles of matter and it is measured in coulombs. So what exactly does that mean? To understand this, let's discuss what do you mean by a matter. A matter is anything which occupies space and has some mass. All solids, gases, liquids or even plasma that we have studied about comes under matter itself. So now, because we know what exactly is a matter, let's understand about it in depth. When you call something as a matter, first thing that you should know is this particular matter is made up of atoms. This is nothing but a simple image to represent atom. These atoms are made up of something called as protons, neutrons and electrons. The charge that we want to understand about is a property associated with these protons and electrons of atoms. When you call something as a proton, it is associated with a positive charge. When you call something as an electron, it is associated with a negative charge. From that, what we understand is protons and electrons of atoms have an electrical property called charge. Okay, it can be positive, it can be negative. And along with that, what you need to know is like charges repel each other while opposite charges attract each other. Now we can see this particular formula Q equal to NE. Whenever you need to find the total amount of charge, you have to just multiply the number of electrons or protons with the charge associated with one electron or one proton. Okay. Here, if you are considering a proton, the charge will be plus 1.6 in 10 power minus 19 coulomb, while if you are considering the electron, the charge will be minus 1.6 into 10 to the power minus 19. The smallest amount of charge possible called as elementary charge, and 1.6 into 10 to the power minus 19 coulomb is the value of that particular charge. Next, what we see is coulomb. Okay. This is the SI unit of charge. When you call something as 1 coulomb, the amount of charge it holds is equivalent to the charge held by 6.242 into 10 to the power 18 electrons. So throughout, I'll be using the term unit charge. Unit charge actually refers to 1 coulomb of charge. So now, if I consider movement of this particular charge, that itself is your current. When a charge moves, we call it as current. And the definition associated with current is electric current is the time rate of change of charge and it is measured in amperes.
What exactly do you understand by this particular definition? Current measures how fast electric charge is moving through some conductor at any instant. Okay, that is, if a lot of charge moves quickly, then it is called as high current. At the same time, if a little charge moves slowly, then it's low current. And we know electric current is measured in amperes, where when you say 1 ampere, it means 1 coulomb of charge is flowing for every second.
And the formula associated with it is given here. I have written I of t to indicate that the current we are considering here is an instantaneous quantity. What do you mean by instantaneous quantity? The current we are considering here varies with time, because of which we have specified t here to indicate time. Okay, so it is given by dq by dt, where q is nothing but the charge and t is nothing but the time. Now if you notice here, you can see an image which shows electrons flowing. We have negative terminal here, positive terminal here. purpose of this image is to show that electron flow direction is opposite to conventional current direction. What do you mean by conventional current? We had a scientist called Benjamin, who was among the first scientists to work on the concept of electricity. Okay, he considered current to be flowing from positive terminal to negative terminal. Okay, but if you consider the actual electrons movement which causes the current, since electron has negative charge, it moves from negative terminal to positive terminal. Okay, but because of the concept introduced by Benjamin, which is used in multiple cases like circuit diagrams, right hand rule, etc., where conventional current direction is considered, what you should know is conventional current direction is always opposite to the direction of electron flow. We have two different types of current, one called DC current, one more called AC current. DC is direct current, AC is alternating current, and the difference between them is, in case of DC, the current remains constant with time, while if you are considering AC current, it is nothing but current that varies sinusoidally with time. Let's be specific that we are considering current in metals. Then the charge carriers which will be flowing are nothing but electrons. So if these electrons are flowing in one direction itself, then we call it as DC current. But there is a chance that these electrons keep oscillating in multiple directions instead of just flowing in one particular direction, then it leads to AC current. Okay, and this is how we represent it. With respect to time, if the current is constant, then it is DC current, but if you see a sinusoidal waveform, then we call that AC current.
Next, we have the concept of voltage. When you consider voltage, the first thing that should come to your mind is electrical pressure. So, this itself is the force that pushes the charge. A stronger voltage produces more current through the conductor. Let's check its definition now. Voltage or potential difference is nothing but energy required per unit charge to move a charge between 2 points in a circuit, and it is measured in volts. Let this be a conductor and this is some point A, point B of that conductor. Okay, if I want to move unit charge, that is 1 coulomb of charge, from this point to this particular point, obviously some energy is required. So that energy experienced by this particular 1 coulomb of charge, or that energy required to move this 1 coulomb of charge, is nothing but voltage. And if you see here, voltage is given by differentiation of energy expressed in joules with respect to Q, that is nothing but charge in coulomb. One more thing that you should know is, if you want to move a unit of charge, okay, through a conductor in a particular direction, we already know it requires some energy, right? Now if this particular energy is provided by a source, then we call it as EMF. That is, EMF is nothing but voltage itself, but offered by a source. But when you call something as voltage or potential difference, it can exist around any element. What it actually means is, if there is some charge here at some point A, okay, this is some point B, the energy experienced by charge, that is unit charge over here, which pushes it and moves it to this particular point B, is voltage or potential difference. But if this required energy is supplied by a source, that is, for example, it could be a battery or a generator or any source for that matter, okay, we call it as EMF. Then we have the concept of electric potential. This is again energy required per unit charge. Okay, so that we move it from infinity to some point A. Okay, so we use the concept of infinity here because we consider electric potential at infinity to be equal to 0.
Next is the concept of power. Since you already know about voltage and current, it's actually product of voltage and current. Now, if you come to its definition, it's the rate of expending or absorbing energy. Okay, rate at which a particular element might be either emitting energy or it could be absorbing the energy. So the rate at which it is carried out is your power and it is measured in watts. Okay, so we have some small derivation here. So because power is time rate of expending or absorbing energy, it is directly written in this format where W refers to energy and T is time. So we can just divide and multiply by dq of T, which gives us with differentiation of energy with respect to charge and differentiation of charge with respect to time. Okay, now this is nothing but V of t and this is nothing but I of t. That's why you will come across something called voltage into current is power. Okay, and one thing you should remember is when you use small letters, they usually refer to instantaneous quantities. DC and average values of current, voltage, power are represented using capital letters. Okay, so here, as already explained, W is energy in joules and T is time in seconds. If you want to calculate average power P over the time period T, then this is how you will calculate that. So this is nothing but your instantaneous power. And then we have a concept of power absorbed and power delivered. Okay, so what do you mean by power absorbed? Usually associated with loads itself, and delivered is associated with source of energy. That is, if you consider a battery is supposed to provide the necessary voltage to cause the electrons to move, correct? Is it supplying energy or is it absorbing energy? It is supplying energy. Okay, while if you consider a bulb, it requires energy to glow. So that is an example for load. Okay, and it absorbs energy. Okay, and how will you identify which component absorbs energy, which component delivers energy? If current leaves the positive terminal, immediately you know here power is supplied or delivered. On the other hand, if current enters the positive terminal, we know here power is absorbed. Okay, if power has a positive sign, power is being absorbed by the element. If it has negative sign, it is being supplied by the element. This is nothing but passive sign convention that you need to know when you learn about power. Lastly, we have the concept of energy. Energy is capacity to do work and it's measured in joules. And even in real life, we use the concept of energy very often to indicate whether we are in the position to do some task. When we say we have low energy, it means we are not in the position to do any task. At the same time, if we say we have enough energy, then it means we can do some task. You might be receiving the electric power bills. These bills actually give you the information about how much amount of energy is consumed by your house. Okay, and it is usually represented in watt hours, where 1 watt hour is 3600 joules. If you want formula to indicate the relationship between energy and power, it is something like this. Okay, it's the integral of power. So that's all about this particular session.